Chapter 9, we are dealing with molecular geometry and bonding theory. So in Chapter 8, we talked about chemical bonds. Now we're just going to continue to talk about chemical bonds, how they bond, and the geometry of bonding. Now in 9.1, in this first section here, this is going to review kind of what we talked about last year when it came down to molecular bonding, and we're going to review a couple things. So remember molecular shapes, excuse me. Molecules are going to have a variety of shapes based on really two things: how many bonds they have and how many married couples or unshared pairs of electrons that are on the central atom. So by counting the number of bonds, or the number of atoms it is bonded to, and the number of married couples on the center atom, we can determine the molecular shape of a molecule. It's pretty simple. So down below there's a bunch of examples. AB2 is linear, AB3 is trigonal planar. So you can kind of see here some examples. Now, what kind of determines it? Well, again, we are determining two things help determine the status of the geometry of a molecule: the number of atoms that are bonded to the central atom, which we phrase as B, and then the number of unshared or married couples on the center atom, which we refer to as E. And there are kind of 5 different basic domains that we kind of call, and they are here. They're AB2 linear, AB3 trigonal planar, AB4 tetrahedral, AB5 trigonal pyramidal, and AB6 octahedral. Now, unfortunately, you're going to have to kind of understand these because these are not given on the test. So, when we talk about this, there's something called electron domains. And electron domains is essentially what we just got done talking about. How many total domains does the center atom have? Well, in this example, there are 2 domains that count: the number of atoms bonded to it. So we have 1, 2, 3, plus we have an unshared pair of electrons. So in this example, there are 4 electron domains. We are going to study electron domains 2, 3, 4, 5, and 6. So when we talk about electron domains in a double or triple bond, it doesn't matter because we're really talking about the number of atoms bonded to the central atom. So that's kind of what it comes down to with electron domains. A, the number of atoms bonded to the central atom, and B, the number of unshared pairs or married couples on the center atom. So we have 4 domains here, and there's a variety of ways those 4 domains can be arranged, and we'll talk about that momentarily. Valence shell electron pair repulsion theory, or the Vesper theory, really tells us what is going to be the best arrangement given the electron domain. So what is going to be the best arrangement given a married couple and 3 domains, or 2 married couples and 2 domains, or 5 bonds and 1 married couple? What's going to be the best possible way? Because remember now, electrons are negatively charged and they are going to repel each other. So these bonds are going to want to be as far apart from one another as possible and equally spaced. So the Vesper theory gives us an idea how that's going to work. Now, if you look at, we're going to go through Table 1. Table 1 is essentially a run-through of how bonds work, all right, and kind of an idea of how it works. We are not going to get set on table 9.4 yet. That's 9.4 in the slide here until section 9.2. So just kind of hang on to that. But what we're going to do is we are going to go through the electron domains for 2 through 6. We're going to show you some possibilities, and we're going to give you the specific names for those electron domains. All right? So, like we just got done talking about, all you need to do is count and figure out the total number of electron domains. And you're going to label it as really A, B, E. All right? A being the central atom, which is pretty easy to number. B is going to be the number of atoms bonded to the central atom. And E is going to be the number of married couples or unshared pairs of electrons on the central atom. All right, what we call married couples or those unshared pairs. So if we have an example here, we have NH3 down below. Its center atom is A. It has 1, 2, 3 atoms attached to it, so it's B3. And as you can note, we have one married couple on the central atom, so in this example it would be AB3E. And we'll go through and explain what shape AB3E should be. Just giving kind of an idea, now the electron domain geometry is not often the shape of the molecule. It's defined by the positions only of the atoms in the molecule, not the bonding pairs. So it may slightly, what we're figuring out may not be the actual identity of the molecule, but it's going to be pretty close. So there's possibility that can be more than one geometry. So as you can kind of see here, we can go from tetrahedral 4 domains to trigonal pyramidal 3 domains to bent 2 domains, all kind of with the same idea if we remove an atom. So with that, let's kind of go through and talk about the different electron domains. So if we have two domains total, couple things with two domains. Anytime you have two domains, it's going to be AB2. The molecule is going to have a 180 degree structure or an angle. The bond angles will be 180 degrees apart. And we refer to AB2 as linear. There is only one possible domain for AB2, and it is linear. So AB2, linear. 180 degree angles between the bonds. Next up, if we look at trigonal planar, and trigonal planar has three possible domains. Now with trigonal planar, the bond angles are 120 degrees. So trigonal planar, the bond angles are 120 degrees. And there are two possible domains for there are two possible geometries for something with three domains. The first one is if it's AB3. The second one is AB2E. And if it is AB3, it is going to be what we call trigonal planar. If it is, trigonal planar. If it is AB2E, we're going to call it bent. So, trigonal planar, there are only two types of possibilities with trigonal planar. Both of these are going to have bond angles of 120 degrees. The two possible characters, or two possible ways, are trigonal planar and bent. So just kind of keep that in mind when we talk about the three domains. There's only two possible domains with three electron domains. So non-bonding pairs are physically larger than bonding pairs because the electrons want to repel each other. So in the married couple, the electrons want to repel each other. Therefore, in the married couple, the repulsion is greater, which tends to decrease bond angles for the rest of the molecule. So what you can see here is that typically what you're going to have is that you can see in the first example here, there are no married couples and the bond angle is 109.5. We throw in one married couple, and the repulsion between here and here becomes greater, which squeezes these two bonds together, which closes that angle to 107. If we add a second married couple, you can see that the repulsion becomes greater on the top, forcing our two bonded atoms together, even decreasing that bond angle more. So if you have married couples in the mix, it's going to affect your bonding angle slightly more. So just kind of something to note there. Same thing here, multiple bonds. Now, one thing that shortened shortened bond length or bond angles was the married couples due to the repulsion. Another thing that's going to shorten bond angles is double or triple bonds. Due to the fact that double or triple bonds draw the atom closer to one another, there's going to be slightly more repulsion. So you can see here where the double bond exists, there's slightly more repulsion than there is with the single bond. Since the double bond is drawing that oxygen atom closer, there's going to be more repulsion between oxygen and chlorine since they're slightly closer to one another than the chlorine and chlorine based on bond length. So there are two things that kind of can affect bond angles. Just I want you to understand that you're not going to ever have to calculate that the bond angle is 111.4 between chlorine and chlorine. You just won't have to do that. But if they give you a molecule like this and they may ask you to explain why the bond angle between chlorine is less than that of carbonate or oxygen and chlorine, you will have to do that. So just kind of keep that in mind. The two things that affect bond angles are double and triple bonds and those married couples. So as we get back to our domains here, 4 domains. There are possible of 3 different geometries for 4 domains. You can have AB4, you can have AB3E, and you can have AB2E2. And the names for each of those, AB4 is tetrahedral. AB3E is trigonal pyramidal. And AB2E2 is bent. Now, with tetrahedral, all the bond lengths on a 4 domain or tetrahedral bond is 109.5 degrees. So, to kind of review, if it was 2 domains, the bond angle was 180. If it was 3 domains, the bond angle was 120. If it's 4 domains, the bond angle is 109.5. So those are the 3 possible domains for tetrahedral, or the 3 possible geometries for the 4 domains. Now if we go to 5 domains, we're going to start talking about trigonal bipyramidal. And trigonal bipyramidal, rather than having a defined angle length, kind of has 2 angles. And you can kind of see the 2 angles that are going to exist. You have one here and you have one here. The bond angles with trigonal bipyramidal are 120 and 90 degrees. So with trigonal bipyramidal, they're 120 and 90 degrees with trigonal bipyramidal. Trigonal bipyramidal is kind of the 5th domain. So you can kind of see how this works. 5 domains. And we already said with 5 domains, the bond angle is 120/90. With 5 domains, there are 4 possible geometries for 4 domains, or 5 domains, excuse me. We have AB5. We have AB4E. We have AB3E2, and it's even possible to have AB2E3. And depending on what those are, AB5, that's easy. The base pair is always what the unit is named after, so this is trigonal bipyramidal. AB4E is a seesaw geometry. AB3E2 is a T-shape geometry, and AB2E3 is a linear geometry. So those are your 5 concerns, or those are your geometries for your 5th domain. Moving on here, 6, domain number 6. What we have when we talk about domain number 6 is essentially this. You have 3 different geometries for domain number 6. By the way, the 6th domain has all 90-degree angles. So the 6th domain is all 90 degrees. And you have 3 possibilities. You have AB6, AB5E, and then you have A, B4, E2. Those are your three possibilities for 6 domain, and if we go through and name them, AB6 is octahedral, AB5, octahedral, AB5E is square pyramidal, and AB4E is square planar. So all in all, you have about 11, 12 different geometries that you're going to have to know based on the domains. So you can kind of have a general idea with that. So domains 2 through 6, you're going to have to know domains 2 through 6 and the different geometries that they have, and it's just kind of work by practice, figuring out what they are and their geometries.